Okay, good morning. Hello, everyone. Okay, so today we will have our uh, exam 2 solution. So I hope you like the questions that we have designed. I think one or two questions are a little bit hard, so don't worry if you have difficulties. So I myself would have also not be able to solve that when I was a student in the class, I guess. But anyway, let's see the questions and the solutions. The first question asks us to solve the recurrence an is equal to 2 times an minus 1 plus 3 times an minus 2 plus 25 times 4 to the power n minus 2. And then we have the initial conditions a0 and a1 to be 1 and 32 respectively. So this should be a fairly easy one because we can apply the standard technique to solve the question. So what we can do here is we can find out the particular solution and also the homogeneous solution for the recurrence relationship. For this particular solution, because if you look at the recurrence, it is so the a linear combination of these an values will give us which looks like 4 to the power n. So it is natural to guess the particular solution should also look like something multiplied with 4 to the power n. So if we start with this assumption, we can plug in our guess into the value of an and an minus 1 and an minus 2 respectively, so that after some manipulation, we can find out that, 5 times 4 to the power n would be a particular solution. So any particular solution works. So we now have this one, so we can proceed with finding the homogeneous one. So for the homogeneous solution, we can use the characteristic equation technique. So we set up the characteristic equation for the problem, which is equal to x squared is equal to 2x plus 3. And then by whatever method you can, or by just eyeball observation, we can see that the roots of this characteristic equation are minus 1 and 3. So for such a case, we see that the homogeneous solution will be of the form some constant multiplied by minus 1 to the power n plus some other constant multiplied with 3 to the power n. And then, based on the particular solution and the homogeneous one, we get the total solution, which looks like this. Now, this total solution has two unknowns, a and b, but we also have two initial conditions. So after somehow we solve that, we find that this a here is minus 6 and this b here is plus 2. So we get the answer. Now, in order to check whether you have done anything wrong, we will be, a good habit is to find out whether A0 works, whether A1 works in this formula, and then we use the recurrence to compute A2 and see whether A2 also works here. So this is a way that we can quickly check if our answer is correct. Okay, this is Q1A. For Q1B, we do the same thing, but this time the recurrence relation is just a linear combination of these an terms, and which is equal to 0. So in that sense, 0 will be the particular solution. So this will make the problem much simpler. And then we have the initial conditions, a0 is equal to 1, a1 is equal to 15. So what we can do here is we proceed with the same idea. We find out that the particular solution, 0 is one of it. And then for the homogeneous solution, we get the characteristic equation to be x squared minus 6x plus 9 is equal to 0. And we find that it has double roots, repeated roots. Now when we have repeated roots, the homogeneous solution will be of a form that is slightly different. So instead of just a times the root to the power n plus b times another root to the power n, it will be a plus bn. This whole thing times the root to the power n. And so we get the total solution. We plug in the a0, a1 value here so that we can solve the two unknowns a and b, and finally we get this one. Okay, so this is a solution for Q1b. Now Q2, is perhaps the hardest problem of this exam. So we have the recurrence an times a 2 times an minus 1, an minus 2, and we have initial conditions a0 and a1 here. So to analyze this problem, first ignore the initial conditions. They are just there to solve the unknowns later. If you look at this recurrence, it is not in linear form. So what we try to do here is there a way that we can transform this recurrence into some other form, and then it will look like a linear recurrence? This is how one can solve it. The trick here is we divide everything by an minus 1, an minus 2. We divide everything by the product. So if this is the case, then we can see that the left-hand side will become an divided by an minus 1. The an minus 1 square term will now become an minus 1 divided by an minus 2. And finally, the plus 2 an minus 1, an minus 2 term will now become just plus 2. And so if you look at this one, then it is really nice that we can try to set Bn to be an over an minus 1. So this is the Bn term here. This will be the Bn minus 1 term here. So we will have Bn is equal to Bn minus 1 plus 2. But then Bn minus 1 will then be equal to what? Itself, it is equal to Bn minus 2 plus 2. So Bn minus 1 plus 2 will become Bn minus 2 plus 4. Is that okay? And then if you look at it, so when it is n minus 2, it will be 4. Is that okay? If it is n minus 1, it is 2. So if it is 1, then it should be 2 times an minus 1, right? And finally, what is B1? Now, B1 is easy. B1 is equal to A1 divided by A0. This time, we are using our initial conditions. A1 divided by A0 is also 2. So in such a case, we can really compute this B1 to be 2 so that this is equal to 2 times n. Now, Bn is a very simple term. It is just 2 times n. But to solve the recurrence, we need to find out what is an. So now to compute an, we can make use of the b terms. So it is equal to, so first of all, it is equal to an over an minus 1, and then I want to cancel this an minus 1, so I multiply an minus 1 over an minus 2, and so on and so forth until I get a1 over a0, and in the end, I multiplied with a0. So we have the calculation here. As long as none of these terms is equal to 0, then it is a valid formula. Okay? Yeah, we will see that none of them is equal to 0. We can argue easily that none of them could be 0. Given a0 is equal to 2, a1 is equal to 4. And this is what? This is Bn term. This is Bn minus 1. This is B1. This is a0. Bn is 2n. Bn minus 1 is just 2 times n minus 1. This B1 term is just 2. So if you multiply everything here, it is going to be 2 to the power n with n factorial. And finally, we see that a0 is just a 2. So in the end, it is 2 to the power n plus 1 multiplied with n factorial. So this is the answer for question 2. And for question 3, we want to show that for any positive integer k, 2020 to the power 2k minus 1 is divisible by 2021. Now, we can solve this easily, actually, by using induction. You see that we can set up the base case as the case when k is equal to 1. And when k is equal to 1, we find out 2020 to the power 2k, which is 2020 to the power 2 minus 1 as our focus. But then we see that this is like some square minus 1 square. So it is equal to 2020 plus 1 times 2020 minus 1. This term is 2021. This term is 2019. For whatever, as long as this is an integer, it's okay. So we see that this whole term is a multiple of 2021. So it is divisible by 2021. And the claim is therefore true for the base case. Now for inductive case, we assume that the claim is true for k is equal to some value of n, whether it is still true when k is equal to n plus 1. So when k is equal to n plus 1, the focus will be 2020 to the power 2n plus 2, and then minus 1. And this term, we just take 2020 square out. We have 2020 to the power 2n inside, and then minus 1. But then by our induction hypothesis here, we have assumed that the claim is true for k is equal to n. So what does that mean? 2020 to the power 2n minus 1 will be a multiple of 2021. So in that case, this whole thing will be a multiple of 2021 plus 1. Is that okay? This inside here will be something like this. This is true. The second line here is true because of the induction hypothesis. And now we can use algebra. So we have 2020 squared multiplied with this one plus 2020 squared multiplied with 1 and then minus 1. So the first part is 2021 multiplied with 2020 squared multiplied with m. And the second part is 2021 multiplied with 2019, whatever, an integer. Okay, so we see that the whole thing is divisible by 2021. So what do we know? We know that assume that the claim is true for k is equal to n, then we can get the conclusion that the claim is true for k is equal to n plus 1 under this assumption. So most importantly, we need to have our conclusion because now the base and the inductive cases are correct. By the principle of mathematical induction, the claim, the formula is correct for all k is equal to 1, 2, 3, up to infinity. Okay? Okay, so this is question number 3. Okay, but then if you have learned basic number theory, or if you have already pre-studied our next topic on modular arithmetic, then we can directly argue the claim is true by using this one. 2020 to the power 2k minus 1. Using modular arithmetic, it will be equal to minus 1 to the power 2k minus 1. If we consider division by 2021 as our modular operation, and now minus 1 to the power 2 is 1. So minus 1 to the power 2k is 1 to the power k, and it is equal to 1. 1 minus 1 is equal to 0. So what does that mean? If you understand what I'm talking about so far, we will find out that when 2020 to the power 2k minus 1 is divided by 2020, we get the remainder 0. So this is how this formula is interpreted. So in that case, yeah, because we didn't make any assumption on k except that it is an integer, so this claim is true for any positive k. So it is done. Okay. Okay, now question number 4. It is perhaps the second hardest question, but it is not that hard if you have enough time to think about it. This question says we are going to select any 16 numbers from 1 to 100. So we don't specify which 16 numbers that we are selecting. We need this to be true for any 16 numbers that we are selecting. The question here asks us, can we always find 4 distinct numbers from the selected number such that they can form 2 pairs? And for each pair, the sum or the difference is a multiple of 25. Yeah, can we do so? Now, if you guess correctly, yeah, this question will be related to the Pigeonhole's principle. So the idea here is we want to divide the numbers. So we want to partition the numbers from 1 to 100 into groups so that for any 2 numbers that we select in the same group, then the sum or the difference will be a multiple of 25. So how can we do so? So this is the idea. So we are going to form 13 groups altogether. We have a label J here. So we have group J contains the numbers of the form 25 times k plus or minus j. So basically, in the group J, we have all the multiples of 25 plus or minus j. Now, if you can double check it, for instance, what are the numbers in group 1? Group 1 will have numbers like 1, 24, 26, 49, 51, 74, 76, and also 99. Now, because each of the number is of the form 25k plus or minus 1, so if we get two numbers, either their sum, if one of them is plus or one of them is minus, either their sum or their difference, if one of them is a plus, another is also a plus, or if one of them is a minus, the other is also a minus, then in such a case, the two numbers from this group, any two numbers from this group, if we select, they will sum up or divide by a multiple of 25. So this serves our purpose. So this is our claim. Any two numbers in the same group sum up or divide by a multiple of 25. And so normal Pigeonhole principle will tell us that if we select 14 numbers, then some of the group will have two or more selected numbers, right? Yeah, because we have only 13 groups. So if we select 14 numbers, some of the group will have two or more selected numbers. And if we go further, one step further, suppose that we're selecting 16 numbers, then what will happen? Then either one of the group will have four or more selected numbers, or we need to have two groups, each of them has two or more selected numbers, because otherwise the total numbers that we have will be equal to something like, there are at most three numbers in one. So we can easily argue we have so many numbers that we are selecting. Actually, we have how many numbers? We have 16 numbers, right? And then we have 16 numbers, we have 13 groups. If we do not have these two situations, what does that mean? So we can only have one group with 3 numbers, and for all the remaining groups, they must have only one selected number. So in that case, we are having only 15 numbers. There is a contradiction. So we can see that either one group has 4 or more selected numbers, or we have two groups, each of them has 2 or more selected numbers. In either case, we are done, because in this case we have 4 distinct numbers that we want to have, and in this case we also have, in the latter case, we also have 4 distinct numbers that we can choose, so that the sum or the difference is a multiple of 25. So finally, this is question number 5. I hope this is going to be very easy for every one of you. So we want to find out 4 ways to select 5 integers from 1 to 9 such that the sum of the squares is still a square. So how can you do so? Because we are having an online exam, so I think you can all have access to some compiler for writing programs. So you can write the program to solve it, and then these are 4 possible solutions. Indeed, there are only 4 possible solutions for this problem. So I hope you can all write the correct program and get the correct answer. Okay, so that's all for all. And then we will still have our tutorial again. Yeah, thanks. And next Tuesday. So see you next week. Okay. Okay, see you. Bye bye.